All right, let's take a look at some historical approaches. I'll go over a list of these, and then we'll talk about some of them. I don't think I do one of these actually. Listwise deletion. Here the idea is we only use complete cases. Mean imputation. Impute mean values in place of missing values. Regression imputation. Impute using regression equations to predict missing scores. A hot deck imputation, something I don't actually talk about later because the hot deck package stopped working or went away. Here we derive imputed scores from similar participants, also known as nearest neighbor. So we find whoever's the most like that person and assign them the score that that person had. Stochastic regression imputation. Regression imputation plus random error thrown in. That's what stochastic means. I refer to this kind of as a gateway procedure because it starts to bridge the gap between these approaches and the next approach. Multiple imputation. Create 20 data sets essentially using a stochastic approach, and then there's other stuff in there. We start again, but it's based on this stochastic idea. Instead of getting one estimate, you get 20 estimates. Maximum likelihood. This is an approach where we actually don't need complete data to do our analyses. We're fine in maximum likelihood, and there's some caveats there. We're fine in maximum likelihood without complete data. The last two are certainly the state of the art now. This is what anybody schooled in quantitative should be using. But let's take a look at some of these procedures, and we'll go through and we'll talk about what's problematic with each of them. First we'll take a look at some data. I just have a very small data set here. I've got the real scores and then observed, what our data actually are. The question marks represent the 3 missing scores. So you can see out of these 10 scores, 3 are missing. What we do with listwise deletion is that we simply don't include those people who have missing data. This is the default for most statistical packages, including SPSS, which means that a lot of people use this approach as a default without having to think about it. R will require you to address the issue. You have to tell R explicitly what you want it to do with missing data. And sometimes, I mean, you could tell it to do listwise, but again, it makes you be explicit. In terms of the results, comparing the actual effect size, mean, and standard deviation to what we get when we do listwise. Listwise is going to kind of reduce that effect size. It's going to tend to reduce the effect size. Not surprisingly, it doesn't have much influence on the mean or the standard deviation. Listwise actually performs reasonably well in terms of accuracy, but the number of cases omitted is problematic. We dropped about 30% of our sample here. Practically, with several measures that comprise lots of items, you might end up losing 40 or 50% of your sample that way. We used to do this and think we were pure and rigorous. Only those people who answered every single question shall be in my data set. But now we know it's a bad choice. I think even more than being a bad choice, one of the major disadvantages here is that it's kind of ethically questionable. If you used people's time for what would be very little compensation, not having their data represented in the data set means that you basically wasted their time. And that's problematic, especially when we have better approaches to dealing with this. All right, mean imputation. If it's missing, just assign it the mean. This is the most common approach historically. And as we'll see with a bunch of these approaches, it starts off, it sounds good, but then when we drill down, what ends up happening is we see, oh, that screws this stuff up downstream. Most software does this pretty easily. You can see here, I've just given the mean to all of the missing values. Here's the mean imputation results. I hate the default coloring here. You can see with mean imputation, the effect size is still down, but what's really important is the standard deviation goes down. And oops, that is a problem because when the standard deviation goes down, remember the standard deviation is a key piece, it's the numerator in fact, for different standard error terms. So when that's getting smaller, what it means is things like our t-value are going to get bigger. So mean imputation is really a terrible procedure that far too many people use. Looking at this, there are advantages. It sounds good if you don't think about it too much. Yeah, what would be more natural than the mean? Well, again, plugging in that mean reduces the standard error. And you can see from the t formula here where that standard error, that denominator is getting smaller, it's going to make the t bigger. And what that does is it increases type 1 errors. All right, regression imputation. Hey, not the mean, but how about a predicted score? I can predict what somebody's score is going to be using multiple regression, or using regression with whatever variables I have in my data set. I can get a predicted score here. Lots of variants for whatever type of regression you want to do. So assigning it the predicted score. What sort of influence does that have? Well, one thing that does is it drives up the effect size. And it also drives down the standard deviation and the standard error. Why is that the case? Well, what regression imputation does is it assigns that exact predicted score to every group, or it assigns the mean of that group to every single individual. So everybody gets to be the mean, and if everybody is the mean, what that means is that the sums of square between group goes up, the sums of square within goes down, and those F values are going to get bigger. So we've really constructed something here that is going to lead to more type 1 errors. More complex approach, not good though. And again, this is another approach that sounds like it should work, but it doesn't. In fact, it's even worse than mean imputation because it has the added bonus of really elevating the effect size. All right, to summarize, classical approaches, they all suck. Most are very terrible, and even more problematically is that most are still widely used. And again, I come back to this point a lot. Just because something is published in a good journal even, it does not mean that it's right. Not every outlet has a statistics expert there to vet everything. There are very few. In fact, I know of only a handful in our field, maybe health psychology being one of the shining examples, where they have someone assigned to check the statistics in every article. Everybody can't be an expert on everything, so that's why we see these persistent problems. Again, just because you see it in the literature doesn't mean people are doing it right.